In this video, I'm going to give the solution of 2008 Step 3 Question 7. Before I give the solution of this problem, I should remind you that this type of question usually appears in Step 3 question paper. Almost every year, they got one complex number problem for candidates who took Step 3 exam. But personally, I dislike this kind of question because it involves a messy calculation of complex numbers and needs you to think critically on the problem to solve it fast and correct. But anyways, let's get into this problem. So the points A, B, and C in the Argand diagram are the vertices of an equilateral triangle described anticlockwise. So we have our Argand diagram and an equilateral triangle. Maybe it's not very nice looking, but it's just used for illustration. So here is our equilateral triangle. Okay, and it's described anticlockwise, so we have A, B, and C. And next, the problem asks us to show that the complex numbers A, B, and C representing A, B, C satisfy 2C equals A plus B plus I times the square root of 3 times bracket B minus A. So this is actually not as scary as it looked, because for the most of Step 3 complex number problems, the first question probably just used the rotation property of a complex number. So recall that if you multiply a complex number R1 by R2, then this complex number R1 will be extended by the multiple of the modulus of R2 and will be rotated anticlockwise by the argument of R2. And most of Step 3 complex number questions just involved the property of this complex number multiplication. So in order to solve this question, we firstly need to observe that the length, I'm sorry, the display. We usually can just interpret complex number by vector. So the displacement vector of AB is just the the displacement vector of AC is just the displacement vector of AB is just the anticlockwise rotation of displacement vector AC by pi over 3 radians. So by noticing this, we can have e to the I times pi over 3 times A minus B is equal to A minus C. Because the lengths of sides of an equilateral triangle are the same, so we can just multiply this e to the I times pi over 3 to represent the rotation by pi over 3 anticlockwise. So by expanding this term using Euler's formula, we have cosine pi over 3 plus I sine pi over 3 times A minus B is equal to A minus C. And for the former bracket, we have 1 over 2 plus I times the square root of 3 over 2 times A minus B is equal to A minus C. And calculating this equality, we have 2A minus 2C equals 1 plus the square root of 3I times A minus B. And by expanding the right hand side of this formula, we have negative 2C, and we move 2A to the right hand side. Negative 2C is equal to negative A, negative B, plus the square root of 3 times I times A minus B, which gives us 2C equals A plus B plus the square root of 3I times B minus A, which is exactly what the problem asks us to show. And the next question is asking us to find a similar relation in the case that A, B, C are the vertices of an equilateral triangle described clockwise. And this is not very difficult. So if this equilateral triangle ABC is described clockwise, then we shall change the position of A and B, which means that this point becomes A and this point becomes B. So we can just send all our B to A and send all our A to B, which gives us a new relation, which is 2C equals A plus B plus the square root of 3I times A minus B. Okay, and let's get into the first sub-question. It says the quadrilateral DEFG lies in the Argand diagram. Okay, so we have a quadrilateral DEFG. So question 9, we have our Argand diagram, and then we have a random quadrilateral DEFG. So D, E, F. Okay, I should put my G here to make this quadrilateral random and link those 4 points. Sorry, I'm trying to make my graph more nicely. Okay, so D, E, F, G, and show that the points P, Q, R, S can be chosen so that P, D, E, Q, E, F, R, F, G, S, G, D are equilateral triangles. So which means we just extend those equilateral triangles using the sides of this random quadrilateral. So SGD, so S is here, and this is the quadrilateral extended. And we have PDE, so PDE and QEF, maybe Q is here, QEF, and RFG. So apparently PQRS we draw is not a parallelogram. So so maybe we need to re-choose those points of Q and S or P and R to make it a parallelogram. What I mean is, if we re-choose the point S, it can be another on another side of DG. I'm sorry. So we have our S here. So this is S, and we have our Q maybe right here. Maybe our Q is here. So our Q is here. This is our Q, and we erase the Q we drawn before. So this is not our Q anymore. Our Q is up there, and we link PQRS, which gives us which gives us a shape that looks like a parallelogram. Maybe it's not exactly a parallelogram, but it looks like it, and this is what we all asked for. And we need to show this is a parallelogram. So the criteria of judging whether a quadrilateral is a parallelogram is to prove that whether PQ is parallel to SR, and simultaneously it has to satisfy QR is parallel to PS. So QR is parallel to PS and PQ is parallel to RS. So it seems very difficult, but it is not. So what we have here is 4 formulas that if you check my previous videos, you should know that a step question usually uses the propositions you proved before, and you use those propositions you proved before to show the results that you are required in the next step. For example, in order to get the result of I, we have to use the result that we derived before, which is obviously 2c equals a plus b plus I times the square root of 3 times b minus a. So so from what we proved before, we can have 4 equations. 2p is equal to d plus e plus the square root of 3 times I times e minus d, and 2q is equal to e plus f plus the square root of 3i plus times e minus f. and 2r is equal to f plus g plus the square root of 3i times g minus f, and 2s is equal to g plus d plus the square root of 3i times g minus d, which is just the result that we proved before. We apply this to those equilateral triangles we have constructed. So if you get this, then this problem should be very easy, because if you look the line PQ is literally equal to Q minus P. Yes, this is just Q minus P. Because we all have the factor 2 right here, so what we can do to make our calculation more simpler, we can just calculate the result of 2PQ, and this helps us not to deal with the very annoying factor of 1/2. So 2PQ is equal to 2Q minus 2P. You can have this if you treat your complex number in the way we treat vectors. And 2Q minus 2P, if you calculated that, you will have so 2Q minus 2P, those E terms are eliminated, so we have F minus D plus, and here we have plus the square root of 3 times I, because it's minus, so 2Q minus 2P. So again, E terms are all eliminated, and we end up with D minus F. And what about SR? 2SR is just equal to 2R minus 2S, which is equal to, so 2R minus 2S, or G terms are all eliminated, so we have F minus D plus, SR, so this minus this, we have the square root of 3i, apparently, so this minus this, I'm sorry, I confused the order of negation. So we have D minus F here, which suggests that PQ is actually equal to SR. So these two complex numbers should be parallel. And similarly, you can have your QR. You can prove your QR is parallel to PS in a similar way. So right here we have 2QR equals 2R minus 2Q. So what is 2R minus 2Q? 2R minus 2Q is just, so F terms are all eliminated, so we have G minus G minus E plus the square root of 3i times okay, let me see. So R minus Q, all F terms are all eliminated, so we have G minus E again. G minus E. And similarly, 2PS is just equal to 2S minus 2P, and this equals, so 2S minus 2P, so D terms are eliminated, so we have G minus E here again, plus the square root of 3i times, again, all D terms are eliminated right here. So we have G minus E again, which suggests that QR is actually equal to PS. So those two complex numbers are parallel as well, which gives us the result of PQSR is a parallelogram. Okay, so we have completed the first sub-question. The next sub-question is saying that the triangle LMN lies in the Argand diagram. Show that the centroids UVW of the equilateral triangles drawn externally on the sides of LMN are the vertices of an equilateral triangle. So what this problem means is that so if we have, so firstly we have our Argand diagram. So again, LMN is a random triangle. So LMN is a random triangle. L M. Okay, let's put N here. LMN. LMN is a random triangle. I shall use black pen to distinguish between the axes. LMN is a randomly chosen triangle, and we choose UVW. So UVW of the equilateral triangles drawn externally. So we have to draw three equilateral triangles, but by using the sides of triangle LMN. So for LM, we have our equilateral triangle like this. So let's mark it A. Sorry, let's mark it A with red pen. And then we have this another equilateral triangle right here, and I will mark it as B, and another one here, and I will mark it as C. And we link all of those points with dotted line. Okay, and we draw their centroids. So we match L and U, match M and V, match N and W. It's just personal favorite to mark U, V, and W. So I mark this is because I want my result to be generalized. So you can change your points, but the results that you get in finally will be as same as mine. So so I will draw my U right here. I will use blue pen to do that. So here is my U, and here is my V, the centroids of this equilateral triangle, and here is my W. And the question is asking us to prove that this triangle is equilateral. It looks equilateral, isn't it? So this might be equilateral. Okay. So just to recall that we have proved a equilateral triangle in a complex plane must satisfy this equality. So what we have to do is just to prove that 2w is equal to u plus v plus I times the square root of 3 times u minus v. So we are looking clockwise here, so we write u minus v and u plus v. So what we have to do is just to prove this equality. And UVW are the centroids of triangle, and the problem is actually provided us a note that the centroid of a triangle with vertices represented by the complex number x and y and z is the point represented by 1/3 times x plus y plus z. So this what we'll have. We will have our w is equal to L plus n plus c times 1/3, and I will move 1/3 factor into to the left hand side, which gives us 3w is equal to L plus n plus c. And similarly for v, 3v is actually equal to is actually equal to n plus b. So I want my ABC terms to be specific. Yes, to be specific, but just to write them in the same way. And 3u is equal to L plus m plus a. And here 2a is actually equal to L plus m plus I times the square root of 3 times m minus L. And 2b is actually equal to m plus n plus I times the square root of 3 times n minus m. And here we have 2c is equal to so 2c is equal to n plus L plus I times the square root of 3 times L minus n. So now because the equality we want to prove is just this, so we have to prove right hand side is equal to left hand side. So in order to make our calculation clear, I rewrite this equality as 6w equals 3 times our right hand side. So 3 times this right hand side. And our left hand side, so let's start to prove this proposition. Left hand side is equal to 6w, and by the equality we listed right here, 6w is equal to 2l plus 2n plus 2c, which equals 3 times l plus n, because 2c is just n plus l, and we have 2l plus 2n here, so we end up with 3 times l plus n, and plus I times the square root of 3 l minus n. So this is our left hand side, and for the right hand side of this equation, we have 3 times u and v. So let's make it more clear. We extract 3 and rewrite our right hand side into 1 plus the square root of 3i times u plus 1 minus the square root of 3i times v. Because I find if we do if we simplify the question, if we simplify the equality in this way, it will make our calculation much more simpler. So our HS is equal to 1 times the square root of 3i times 3u, and 3u is just L plus M plus A. And here we again have plus 1 minus the square root of 3i times 3v, which is just M plus B. And now we expand those two brackets by substituting the values of A and B. So we have 1 plus the square root of 3i, so times L plus M plus, so A is equal to 1 over 2 times this right hand side. So we have 3 times L plus M over 2 plus I times the square root of 3 times M minus L over 2, and then plus I minus the square root of 3i, and we do exactly the same, which is 3 times M plus M over 2 plus I times the square root of 3 times M minus M, just substituting this 2b we have right there, and divided by 2. And now we extract our one half term in front of our right hand side, and we substitute those things in. So we have 3L times 3M. So we firstly multiply this by 1 and then by square root of 3i. So here we have 3L times 3M times the square root of 3i times M minus L, and then we have plus 3 times the square root of 3i times L plus M, and plus, so square root of 3 squared is 3, and the square of I is -1, so we have negative M plus L. Okay, oh sorry, negative 3M plus 3L. Oh, and for the next one, we have plus 3M plus 3M plus the square root of 3i times M minus M plus, sorry, it's not plus, it's minus the square root of 3 times the square root of 3i times M plus M, and plus 3, sorry, and if we multiply those two terms, we have so negative signs and i's are cancelled and they become plus, so we have plus 3 and plus 3 and minus 3m. End of the rectangular bracket. And now let's see things that we can cancel in this equality. So this 3n is cancelled with this 3n, and this 3m is cancelled with this 3m, and this square root of 3 times I times n is cancelled with this minus 1, and this m is cancelled with this negative 1 as well. So what we will have here is 1 over 2 times 6l plus the square root of 3i times negative l plus 3l. And we have plus, so we merge those two terms, and we merge those two terms, and we have plus 3n plus the square root of 3i times so here we have n minus 3n. Yes, I believe this is correct. So what we'll have here is just equal to 3 times l plus n plus the square root of 3i times 2, sorry, it's not 2 is multiplied by 1 over 2, which becomes 1. So it's l minus n. And let's see, the right hand side is exactly equals the right hand side. Left hand side is equal to right hand side. So we have proved that UVW is indeed an equilateral triangle. And this is the end of this video.